In the past few lessons related to Kirchhoff system review, we've mostly stayed within one energy domain, right? And this has allowed us to review the basic principles in each of these areas, and it's important to feel comfortable as we move into more complex systems with those different areas, because we'll start looking at models that have interactions between those energy domains. And before we get there, wanted to talk about a couple of different aspects of models that you're familiar with, and just again in terms of categorizing, I decided to put this under sort of interactions between these different Kirchhoff systems. And one way that we have that is really what makes, in my opinion, sort of system modeling interesting, and really the creation of machines through what we're going to call ideal couplers. And as you can see, I've kind of put, again, more examples of what I'm talking about here. Ways that we can transform, and I hope you recognize, I have a power connection on one side of a lever, for example, and this lever could represent a lot of different things, but it really is representing sort of a mechanical to mechanical transformation. The basic lever is obviously a simple one, but the idea behind all of these little basic machines, if you want to call them that, is that what we're trying to do is isolate what we're going to call the ideal, power conserving transformation, right? So as opposed to all the other basic elements that we've looked at, which have had one port, these are all two-port representations, or two-port elements, if you like. So here's a gear set, right? You can think of this as a system, and there's power coming in, and then there's power coming out, and in the power sense, positive in and positive out, but again, power could flow in both directions on all of these. So you could stay within the same energy domain. Here's an example of that, and here's actually a little practical example of a little lever. But you can also transform across different energy domains. So here, the piston, obviously you're in one domain. Here you're mechanical, and here you're fluid. So you can see how we're using these elements to model those familiar machines that you have worked with, that represent a large set of practical engineering problems. And I've included a little sprinkler here to really show kind of a turbo machine where you have rotational dynamics interacting with fluid, right? So the pumping action. This basic analog meter movement, the basis for the relationship between electrical domain and really there's an interaction between several domains here. If you think about electrical, there's magnetic, and then there's mechanical rotation, but we can think of it as just being electrical to mechanical, so it's an electromechanical device, unless we were really specifically going to study the magnetics. This also shows an example of that, where you have an electrical port here and then a mechanical port, and we'll look at those briefly. So again, ideal couplers represent power conserving transformations. What we mean is that we're abstracting away from a device only that part that represents the lossless transfer or transformation of energy or power from one part of the system to the other. This means that those parts of the system, for example, that represent storage of potential kinetic energy or dissipation, friction, that kind of thing, we're sort of stripping that out, and we're only looking at the ideal part. So if we're building a model of a pump, for example, we would first identify what is the basic ideal coupling element, and then we would sort of dress up that model with the realistic effects, right? I have a little definition here of an ideal coupler is a physical system where there's a constitutive function, a relationship between these port variables. So I'm now showing this now in a word bond graph form, and this coupler here could be a lot of different types of things, but what we're looking at is power on one port and power on the other port. What this means here is that the net sum of power entering the system, this is the system. It basically means that the power at port 1 equals the power at port 2. And keep this little relationship in mind. That's the power at 1 equals the power at 2 relationship, because it's central to deriving the basic relationships that we'll need to represent the ideal transformation between two parts of a system. Let's look at some examples, starting off with the simplest one, the ideal mechanical coupler being a lever. And I like this little figure of Archimedes showing, in one of his well-known quotes, "Give me a place to stand, and with a lever I will move the world." Again, Archimedes is associated with the study of and definition, right, of basic machines, and the lever being one of them. So when we talk about this lever action, and again, this could take a lot of different forms in realizing it within a machine. We're assuming that we've got ideal transformation between F1 V1 and F2 V2. Sorry, these are small v's, these are large v's, but you see the point that this is a power port and this is another power port representing this lever. Yes, there could be friction at the lever, there could be bending, there could be weight, but again, those things will be added out here. All we're worried about is this ideal transformation, and the way we go about doing that is looking for a basic relationship between the variables through dynamics or kinematics, and then using the power transformation to help us either confirm that relationship or to actually find the other relationship, because there's always going to be two relationships, and as I'll show you shortly. Even Archimedes knew that power coming in was equal to the power going out. So like here, you could even start with that relationship, since you know kinematically that V2 has to equal to L2 over L1 times V1. You could then find the relationship between the forces, or vice versa. You could start off with the force relationship through a static relationship, and then you could find the velocity relationship, right? So that's where you would find out that you had this sort of relation between the velocities and the forces. Same kind of analysis would hold for a basic gear pair. Again, friction is here, inertia, but we're looking at just the basic transformation. You can go back if you've had a machine design course and recall that you can relate through the definition of the diametral pitch and so on, that when you have meshing gears, you can find a nice little relationship between the angular velocity. So what you would do is you'd say, well, I want to represent the ideal gear train transforming power, so I have torque 1 times omega 1 equals torque 2 times omega 2. Since I know that omega 2 is R1 over R2 times omega 1, by then using this other relationship with the power, you would find your torque relationship, right? You could have also done this with a torque relationship, but it's easier to use. Sometimes it's easier to use the kinematics and then use power to find the other relationship in between effort variables, or sometimes the other way around. So now you have your two basic relationships. And note here, this is an effort to effort relation, so these guys are related. I'm using a word here to say, oh, there are gears. Later when we get to bond graphs, we will represent this with more formal symbols. Again, we're just slowly defining bond graphs as usual, and we'll just continue to use words. Also keep in mind, sometimes when you're building this within a bond graph, we will go ahead and assign power flow. So let's say you had a motor putting power positive in, we would have our arrows coming into the gears and then positive coming out. Hydromechanical coupling, we know that there's a relationship kinematically in the flow, let's say, between velocity and flow rate. So given that we want to conserve power transformation just between the flow motion and the piston motion and the flow motion, then we can apply power conservation, and we could then come up with the other relationship. And here is basically the two that we know. We know that force would be related to pressure through area, so we can come up with one relationship. Then we could find the other, and vice versa. These for the piston, it's these two relationships are usually a little bit more obvious, right? So velocity and flow rate are related, force and pressure, and that's a basic piston device. Sometimes we call these, in the machine context, positive displacement devices. A lot of these hydromechanical coupling elements are positive displacement in that sense that you have a volume motion related, a piston motion or mechanical motion related to flow motion. Those are usually categorized as positive displacement type machines, and those form the working principle for a lot of machines. I'll show you a few here. Basic positive displacement piston machine, right? We're talking about just modeling, in this case, just the piston action. In order to make this machine work right, we'd have to drive the piston back and forth, and also we'd need to have, in this case, if we were pumping fluid, say up to a higher pressure, we'd need to have these little check valves that would allow, as you draw flow, as you draw the piston back, flow comes in, and then when you put the piston back down, that closes this one and allows the flow to go out that way. Same way, when you draw this back, it closes this one, so you're not drawing back from your supply side. Okay, basic piston type pump. Here are some other positive displacement pumps, and sometimes we'll abbreviate these as positive displacement machines, if you like. And these can be pumps. Remember, these can be pumps or motors. So you can either drive them. If you drive it, obviously, from torque, from the torque side, you're pumping. If you're driving it from the hydraulic side, then you have a torque, like a torque motor or a piston type motor. And these are just additional examples. Sometimes, again, what we're trying to do is represent the ideal relationship, and you could be given information about these by a manufacturer, and usually you might be given the quantity D, which is sometimes called the displacement, and that has units of say inches per revolution. So this would imply to you that you have a relationship between flow and angular velocity, say if this was a rotational machine, and by imposing a power conserving constraint, you can find the torque pressure relationship, right? So again, this is only modeling the basic ideal transformation, and here's a lot of different kinds of machines. Two kind of rotating lobes, positive displacement machine, and this really is more of a piston type machine where you could have even an angular plate here where you could adjust the displacement. So there are a lot of different types of hydraulic machines, and maybe within the homework I will give you some examples and opportunities to study some of these within a system context as well. The ideal mechanical coupler allows us to now look at interactions between electrical, magnetic, and mechanical, but what we'll do, as I'm showing in this basic word bond graph, is the interaction will be just between the two energy domains, the electrical and mechanical. If we were to study the magnetic domain, then we might look at the magnetic design of the system, but for a lot of practical applications, it's good enough to look at it sort of at a macroscopic level, so that we only have to worry about the interaction between electrical and mechanical. So just like for the other basic ideal coupling elements that I've shown you, you can go and do some simple analysis to prove that at the end of the day you have an interaction between the mechanical and electrical variables in a certain way. So in this case, for example, the induced force on a conductor that's sliding along these other conductors, and maybe you're pumping current through here and back, so you're building a circuit. At the same time, there's a magnetic field, and there's assumptions made here. We would assume that we have a uniform magnetic field, so that B field is constant. You can show through basic Lorentz law that you could relate the force on that moving conductor and note the current. So this is an effort variable in mechanical, and this is a flow variable in electrical. You can also find that you would have a motional EMF here through the basic physics relations, and note again, you have an effort variable in the voltage across here and a flow variable. So we've introduced a different kind of coupler, and I'll show you a classification shortly. But given this one relationship, again, between the force and the current, if I now impose an ideal transformation, which means there's no losses, and I'm not concerned about any energy storage in here, because I may deal with that separately, I would then find the other relationship, which you can see that these two are compatible through power. You might prove that to yourself. So these, most electromechanical couplers, you'll find that comprise most electrical machines. All electrical machines basically relate, either torque, angular velocity, or force velocity to voltage, current. And so this forms a really nice, simple way to model those kinds of devices, as I'll show you in some examples and then the homework problems. So basic electrical motors, we will have a little EM coupler in here to represent that basic element. So this allows us now to introduce a classification of couplers. We saw several where the relationship between the variables was such that, looking at the basic physics, you had effort relationships. So you had a effort on one port related to the effort on the other. Likewise, the flow was related to the flow. These types of relationships, and the M here represents some physical variables maybe, we're going to classify those as transformers, right? Like the basic piston, lever, piston machines, and in the device that we just saw with the electromechanical, we saw that we had an effort being related to through the basic physics to the flow variables, right? So whenever you have that kind of cross relationship between efforts and flows on the two ports, right? So effort 1 here is related to flow 2, and effort 2 is related to flow 1. When you have that cross relationship, we're going to classify those as gyrator elements. Okay. Another important point is that these relationships that we might find through analysis or by being given data, the M or the R, and we'll call these modulus, singular, or moduli, it might not be constant, and in those cases we'll say that they could be changed by another variable, or we'll say that they're modulated. So for example, the B field in this electromechanical coupler was constant if the magnetic field is uniform and it doesn't vary, but it could also be changed if it was, say, dependent on some other electrical circuit generating a magnetic field that you might vary independently. So we'll say that this modulates these couplers. Okay, so we'll call those modulated transformers or modulated gyrators. It doesn't change the fact that the power of that being transmitted across them is still equal. What's happening, and we'll show that. We talked about using power bonds versus signals. We'll use signals, full arrows versus half arrows, right? So the power across these guys is still going to be equal, but we're going to use the signal to show that there's modulation, right? We're going to use that as a modulation signal. I'll show you one example of a modulated transformer, and that's a simple slider crank mechanism. If you do the analysis on this device, you'd find that the velocity of the piston is related to the angular velocity of the crank. But what you'd also find is that M here would be a function of theta. So M through the analysis would be a function of theta, where theta is the actual position of the crank. So what that's saying is that yes, torque is related to force and velocity is related to angular velocity, but you would have so for example, you'd find that there was a function here that depended on the position. So we'll say that that's a modulated transformer. And remember, it's a transformer because you found that the flows are related and thus the efforts are related. Okay. There are examples of modulated gyrators, some electrical motors, but one that's of special interest to mechanical engineers might be the fact that pumps such as dynamic pumps. We talked a little bit about positive displacement pumps, but what we call dynamic pumps, sometimes we might call these Eulerian turbo machines, or turbo machines of different types, like centrifugal pumps, axial flow pumps, mixed flow pumps. These end up, when you do the detailed analysis, which I won't show here, but if you recall from your basic fluids class, sometimes a turbo machine such as this, like that sprinkler, is used as an example to show how the torque is related to the flow going through the machine, and there's a little cross product in there because this is a moment of momentum. When you go through the analysis on machines such as this, you find that these are probably some of the most complicated gyrators that exist. You find that the torque is related to flow rate through the machine, and the modulus here, the little r. Remember, before we had just a constant r. We said it could be modulated. It turns out that for centrifugal type machines, it's modulated not only by angular velocity, how fast the impeller is turning, for example, but also how the flow going through there. So once you find that relationship, and you can derive that from basic principles and given the geometry of your blades and so on, and remember, this is the ideal transformation. There are all kinds of losses in here that really can only be found most of the time, experimentally, if not through complex computational models. Even those would be approximate because of the need to use different turbulence models, but there's losses, yes, but for the ideal lossless power transformation, we always assume that the torque omega coming in is equal to the pressure flow, and so that would allow you to find the other relationship, which is kind of nice. So remember, effort related to flow, and what's complicated about it is that little modulus is a function of those variables. And this is again a fluid machine classified as a gyrator, and we might show that in a word bond graph this way, where this, remember, this is the signal that would say, oh, this guy is going to depend on both omega and q. Sometimes we would show it this way as a signal, two independent signals coming in, actually not just one, that would change how that power transforms across that machine.